Following is a good example to illustrate how useful bus concatenation is. W1 and W2 are two 16-bit vectors, both of type wire. And we want to make the following connection between the two wires, whereby we drive values onto W2, and we can do that using this assign statement. Our objective is to determine what expression to use on the right hand side of the assignment. If we look at the connection shown, we can note the following. The lower 8 bits of W2 connect to the upper 8 bits of W1, and the upper 8 bits of W2 connect to the lower 8 bits of W1. In effect, we are swapping the upper and lower 8 bits of W1 to make this connection. A simple way in which we can capture this in Verilog is to use bus concatenation. So we've got our curly bracket, opening curly bracket and closing curly bracket. Now we note with W2, this refers to a 16-bit vector, and the low order 8 bits of W2 will be assigned to the low order 8 bits of the expression on the right hand side. And the low order 8 bits we want when we make the assignment to W2 are represented by W1, 15 down to 8. And the upper 8 bits of W2 are connected to the lower 8 bits of W1. So the upper 8 bits on the right hand side must represent the lower 8 bits of W1. And the lower 8 bits of W1 go from 7 down to 0. Now we have two expressions. Let's separate them with a comma, and we terminate the assignment with a semicolon. So just to be clear that this is correct, W2 refers to the 16-bit wire. The most significant bit is W2 15, and the least significant bit is W2 0. So the least significant bit connects to the least significant bit of this 16 bits, and the least significant bit is given by W1 bracket 8. And you can see when we look at our connections, W2 bracket 0 refers to this wire, and W1 bracket 8 refers to this wire here. Our assignment makes the connection as shown between those two. And so on, as we move through the bits in here, we make connections to the corresponding bits on the left hand side. Bus replication involves the bus replication operator, and we can describe it as follows. We start with the bus concatenation operation. So we've got a number of expressions. We can have one or more expressions separated by a comma and enclosed with curly brackets. And this is the bus concatenation operation. And what replication does is it causes the expression formed by the bus concatenation to be repeated a number of times. And that involves specifying a replication constant, which is an integer value, enclosed with curly brackets. Let's look at some examples. Taking the following declarations, we've got a single wire W1 and an 8-bit wire interrupt. The following examples use bus replication. In this example, the concatenation involves a single expression. It's just the wire W1. And that expression then is repeated 4 times. So the size of this expression is a 4-bit value, and the value for W1 is repeated 4 times. So this is really equivalent to the following, taking W1 and repeating it 4 times. So bus replication provides us with a compact way to do the same thing. And if, for example, the wire W1 holds the value 1, this expression evaluates to 1, 1, 1, 1, a 4-bit value. The next example involves taking the concatenation described here and repeating it 4 times. concatenation part involves two expressions, W1, which is a 1-bit value, and interrupt 2 down to 0, which is a 3-bit value. So you've got a 1-bit and 3-bit giving us a 4-bit value, and that 4-bit value then is repeated 4 times, giving us a 16-bit value. And for the last example, our bus replication part is shown here. What we've got is the expression due to the concatenation first of all. So we've got interrupt 2 down to 1. We've just got a single expression for the concatenation, so that's a 2-bit value. And then we repeat that 2-bit value 8 times, giving us a 16-bit value. In this example, the result of the bus replication, which is our 16-bit value, is then used as part of the concatenation operation. A 15-bit value, 16-bit from our bus replication, and a 1-bit here. And those 3 expressions are concatenated or joined together to give us a 32-bit value. So this last example uses bus replication as an expression which is part of a bus concatenation expression. There is an important point regarding bus replication. Unlike the bus operations on previous slides, bus replication cannot be used on the left-hand side of an assignment, and this means it cannot be used for output port connections either. The code shown in this module can be used to explore the vector operations and the different integer constant formats. It looks like a test bench in that we have no input or output ports, but we don't have any module instantiation inside this module. Instead, we just have an assign statement. The initial construct contains a monitor task which allows us to view various values as the simulation runs. And we have a number of statements with delay controls, so we can change the reg variables at various points in time. The monitor task outputs the current simulation time using $time, and the output string contains format specifiers. %b indicates binary, so we have 4 binary format specifiers and a 5th format specifier which prints out a decimal value. And the corresponding arguments for these 5 format specifiers are listed here: status, s, data, control, and control. So we print control out twice, once in binary and once in decimal. And the output when this simulation runs looks like this. So take a look at the output, see that you are happy with the values outputted, and you can make changes to the assign statement to explore the various vector operations.